All right, let's talk about one of the most fundamental ideas in all of modern physics, but one that often gets hidden behind the scenes. We're talking about Hilbert space. It's the mathematical arena, the stage where all the weird, counterintuitive rules of quantum mechanics finally, somehow, start to make sense. And today, we're going to build it from scratch.
This was the central question that physicists were wrestling with in the early 20th century. The quantum world just refused to play by the old rules. So, the old math, the world of Newton and Euclid, it just wouldn't cut it anymore. They needed to find, or maybe invent, a whole new kind of space for reality to play out on.
So let's start right there, with the puzzle itself. Why did the math that had worked so perfectly for centuries just completely fall apart when it came face to face with the quantum realm? Well, it really boiled down to three non-negotiable demands that reality was making. First, you've got superposition, this bizarre idea that a particle can be in many states at once. So we absolutely need a space where we can just add states together. Second, to get any useful answers, like probabilities, we need a sense of geometry. We have to be able to measure things like lengths and angles between these states. And third, and this is the really subtle part, we need our math to be reliable. If we run a calculation that's supposed to get closer and closer to an answer, we need a guarantee that the answer actually exists in our space. No exception. Okay, so how on earth do you build a mathematical world that can handle all of that? Well, we're going to do it. We are going to forge this arena, step by step, starting with the most basic quantum need of all. The very first physical requirement comes straight from that core principle of superposition. A quantum particle isn't just here or there, it can be in a combination of both. So that means the mathematical objects we use to represent these states, they have to be things we can add up and multiply. And the mathematical answer to that? It's a vector space. This is the perfect starting point. It's a structure that gives us all the rules for adding and scaling vectors, which are going to be our quantum states. But, and this is a huge but, a vector space all on its own has no geometry. There's no length, no distance, no angles. It's kind of like a floppy, shapeless skeleton. So that brings us to the second requirement. To do any real physics, we have to calculate probabilities. And in quantum mechanics, the probability of, say, measuring a particle in state A when it started in state B depends on the overlap between them. And to measure that overlap, we need geometry. We need to know the angle between those two state vectors. So, to give our shapeless space some structure, we introduce our second ingredient, the inner product. You can think of it as a seriously souped-up version of the dot product you might remember from high school. It's a function that takes two vectors and spits out a single number that tells us everything about their geometric relationship. And just like that, with an inner product, our vector space suddenly has shape. We can now define length, and we can define angles. Okay, we have our algebra, we have our geometry, but there is one last, absolutely critical piece of the puzzle. When we're doing physics, we're constantly dealing with infinite processes, like watching a system evolve over time or breaking a state down into an infinite sum of simpler states. We have to know that these calculations don't just break. The answer we're approaching has to be a real, valid state that actually lives inside our space, not in some void it forgot to include. The mathematical fix for this is a property called completeness, and it's a huge idea. It essentially guarantees our space has no holes or missing points. Imagine you have a sequence of vectors that are getting closer and closer to each other, like they're all marching towards some specific destination. Completeness is the promise that the destination point actually exists within the space. It patches all the potential holes, making our arena solid and totally reliable. And the difference here is just night and day. Without completeness, the whole beautiful structure of quantum mechanics just collapses. As you can see on the left, everything falls apart. Core calculations fail, our tools break, the theory can't make predictions. But with completeness, on the right, the structure is solid. Measurements work, time evolution is reliable, physics works. This isn't some optional extra, it is the glue holding the entire theory together. So, we took a vector space to handle superposition. We added an inner product to give it geometry. And we demanded completeness to make it reliable. And with all those pieces finally assembled, we can give our magnificent arena its proper name. This is a Hilbert space. The definition is so elegant and so concise, it's simply a complete inner product space. That's it. It's the powerful structure that the mathematician David Hilbert developed while trying to figure out how to take the familiar, comfortable ideas of Euclidean geometry and properly extend them into the wild world of infinite dimensions, which is exactly what physics is. Okay, so we've built it. What's the payoff?
What does having this Hilbert space actually let a physicist do? Well, it provides a set of incredibly powerful mathematical tools. It's like a brand new workshop.
So let's look at the crown jewels in this new toolkit. These three theorems are really what make quantum mechanics a predictive functional science. And while they're all crucial, we're going to focus on two that are absolutely essential for understanding measurement: the projection theorem and the king of them all, the spectral theorem.
First up, the projection theorem. This is basically what lets us perform a measurement in the first place. It gives us a guarantee that we can take any quantum state and just cleanly break it down into the piece that corresponds to our measurement outcome and another piece that's totally separate from it. It's how we can precisely split up reality to analyze it.
And now for the big one, the spectral theorem. This is the reason observables, things we can actually measure, like energy or momentum, even exist. You can think of a mathematical operator as a question, like, what is the energy of this system? The spectral theorem guarantees that this abstract question can be broken down into a complete spectrum of all possible, real-numbered answers you could get in an experiment. It's the magic bridge from the abstract math to the concrete results in a lab.
So you might think, okay, story's over. We built the perfect arena for quantum mechanics. But there's one last, really fascinating twist. It turns out that for some of the most useful concepts in physics, even the standard Hilbert space isn't quite enough.
Here's the problem. Physicists love to work with idealized states, right? Like a particle that's located at one single perfect point in space. It's a super useful idea. The trouble is, the math for a state like that is ugly. It has an infinite spike, and it fails a key test. It's not square integrable. And that's just a technical way of saying the total probability doesn't add up to 100%, so it technically can't be a member of our carefully built Hilbert space. So where do these things live? Well, the solution is this even more sophisticated, beautiful structure called a Gelfand triple, or sometimes a rigged Hilbert space. And the idea is just brilliant. You don't throw out the Hilbert space. Instead, you sandwich it between two other different spaces. This is the setup, and it's so elegant. In the middle, you have a space of really nice, well-behaved physical states. That space is nestled inside our Hilbert space, which is where all the probability and geometry rules work perfectly. And that space is then contained within a much bigger, more flexible space of distributions. And that's the proper home for those really useful but mathematically messy idealized states. This framework from Israel Gelfand gives everything a home. So let's just recap that logical chain one last time, because it's so clean. Physics demanded superposition, which forced us to use a vector space. Then it demanded probability, which gave us an inner product for geometry and a way to measure distance. And finally, it demanded reliable math, which forced us to add completeness. And when you put all of that together, the inevitable result is a Hilbert space. I want to leave you with this fantastic quote, which is about the legendary physics textbook by Landau and Lipschitz. It just perfectly captures the role of this whole structure. The foundational books, they often just jump right in and start doing quantum mechanics. They never say Hilbert space. But lurking underneath every single calculation is the silent, assumed bedrock of a complete Hilbert space. Every step they take would fail without it. You know, this entire journey, this incredible mathematical construction, was forced on us by what experiments were telling us about reality. Which just makes you wonder, doesn't it? As we push into the next frontiers, into quantum gravity, or the nature of space-time itself, what new physical principles are we going to find? And what new, even stranger mathematical arenas will they demand that we build?